So now we will talk about large structure in graph. So what are the large structure? You want to say you want to find the condition which ensures subgraph of G which is large. So when can we find a specific, say, spanning subgraph or near spanning subgraph? For example, what kind of spanning subgraph can we consider? Perfect matching or Hamilton-type are good example. And in undergraduate graph theory, we learned about some sufficient condition that guarantees perfect matching and Hamilton-type. For example, we learned about Hall's theorem that if you have a bipartite graph, and if you know that the neighborhood of every set in A, every subset of A prime, you consider the neighborhood of it, and it has size as large as A prime, and there exists matching covering all A. In particular, if A and B have the same size, you get a perfect match. So that's what we learned. And also regarding Hamilton cycle, we learned about Dirac theorem. And if you have a n vertex graph, and the minimum number, minimum degree of n is at least up and n is at least 3, then G contains the Hamilton cycle. So this is a type of statement that we are looking for. When there is some minimum degree condition, then can you find the spanning subgraph? Note that this minimum degree condition is natural. Because if you just think about number of edges, and we don't get good bound. For example, if you consider n-1 vertex complete graph with one isolated vertex, then it has what? n-1 choose 2 edges, which is very close to maximum possible number of edges in n-vertex graph. However, this doesn't contain perfect matching, either perfect matching or Hamilton cycle. So if you want to say find any connected spanning subgraph, then it's impossible to find it here, even if the number of edges is extremely close to maximum possible. And that's due to this isolated vertex. So this local restriction on the degrees can ruin everything. So considering minimum degree makes more sense for this type of question. So we say this is a Dirac-type question. We want to find the minimum degree condition that ensures certain spanning subgraph. So there are many such graphs we can consider. One of them is a generalization of this perfect matching. So what's perfect matching? Perfect matching is disjoint union of K2 covering all vertices. Okay, so there are several ways to generate this. What's one natural way? What if we take, instead of K2, what if we take, say, K or KR? So for example, you can consider this disjoint union of triangle that covers every vertex. That's also quite natural. So in general, we say that this is H vector. In graph G is a subgraph of G. Which is disjoint union of copies of H that covers all vertices of G. So perfect matching is K2 factor. And one natural question we can consider it, what if we consider KR factor? What minimum degree condition guarantees a KR factor? And there is this famous theorem by Hajnal-Szemeredi. On n vertex graph G as let's write it this way. Satisfies that the minimum degree is at least 1 over R over 2, 1 over R times 2, and this G contains exactly n over R floor copies of the vertex disjoint copies of AR. So if n is divisible by R, then you get a AR factor. If it's not divisible by R, then there is no way that you have a KR factor. But you have almost KR factor in a way that the number of uncovered vertices is as small as possible. And this has actually another point of view by considering its complement. So if you have a KR factor in G, then what does it become to in complement of G? If you flip the edges and non-edges, and those clique becomes independent. And it's like a partition of the vertex space into independent sets. That's the proper coloring. Moreover, we have one more condition that every color class here, the independent set, have the size exactly R. In terms of that, we have this concept. We say that a coloring F, the vertex coloring with the K color is an equitable coloring, equitable K coloring. If it is a proper coloring, such that the sizes of the highlight classes are as close as possible, as same as possible. Means that it differs by n most 1. So this can be rewritten as the following. If you have n vertex graph, G has a maximum degree less than k, then there exists an equitable k coloring of G. So that's by considering its complement, these two are the equivalent one. So we will prove this statement. One thing is that we can assume that n is divisible by r, because okay, so here we used r and here we used k corresponds to this. Okay, sorry. So we first claim that we may assume that n is kr. Why? So we now want to show that you have a equitable k coloring. And if this is not the case, then if say n is n minus n k prime modulo k, then we consider G is joint union with k sub k prime. And then if G union k sub k prime has k equitable k coloring, and that's equivalent with G has an equitable k coloring. It's easy to check. If that has equitable k coloring, and every color class has the same size, and then the vertices here are scattered into k prime color class. We delete them, and we get the resulting equitable k coloring. And then if you have a equitable k coloring on here, and there are k prime many color classes with the size 1 less, and we assign each vertex of this in those color class arbitrarily, and you get the equitable k coloring for this joint union. So these two are equivalent. So we can, if n is not divisible by k, then we just arbitrarily add this complete graph on k prime vertices to assume this holds. Okay, and one more thing. Let's say that a coloring f tending these vertices into bracket k, we say that this is near equitable k coloring. If it is a proper coloring, with color classes of sizes r minus 1, r, and r plus 1. So everything is as close to r as possible, but one class has smaller size and one class has large size. Then we say that it's near equitable. So now we want to prove this. And assume we have a minimum counter example. G, which has no equitable K color. So here minimum in terms of number of edges. So if we have a smaller graph with smaller number of edges, then this statement holds. But now G is the minimum counter example, so it doesn't have a equitable K coloring. But every subgraph of it does. And what happens is if you take a G and then you choose arbitrary edge and you delete, then this resulting graph still has a maximum degree strictly smaller than K. So it has a equitable K coloring, which partitions the vertices into K color classes. Each of them has size R. And if now we put back this H, U, V, if U and V belong to different ones, then this same thing is also equitable K coloring of the original graph G, which is a contradiction because it doesn't contain any equitable K coloring. That means two of them belong to here. Then what you do is you take this one and then you move to somewhere else. As this vertex has maximum degree at most K, I mean less than K, there are K parts. This already has one neighbor here. And if it has neighbor in every color class, then it gives you degree K, which is a contradiction. So there must be one part which it doesn't have any neighbor, then we move it to there. Then we get the proper coloring with the size, color class size R-1 here. Everywhere else is R. This one particular class has one large size. So we know that such a graph G admits near equitable K color. Now, by the way, I mean, I forgot to mention that the proof that we are going to show is by Kirstead and Kostochka in 2008. This is further proof that they found. The original proof is more complicated. Now we know that it admits a near equitable K coloring. And out of many choices of this near equitable K coloring, we want to find the one that satisfies certain good properties. In order to describe those properties, let's give some definition. If you have a near equitable K coloring F, let B1, B2 to BK be the color classes. With the B1 being the smallest one and BK be the largest one, and then the rest of them at the same size. What we do is we consider a digraph, directed graph DF with the vertices say B1 to BK. Each color class is a vertex here, and such that what do you want to encode? What information do you want to encode is that we add a directed edge from Vi to Bj if we can move one vertex from Vi to Bj. So roughly, here what we want to do is here we have one more vertex, here we have one less vertex. If there is some vertex here that we can move to here, then we will be happy. That will give you equitable coloring. Or if there is one vertex you can move to here, and then another vertex you can move to here, And then another vertex you can move to here. Then you move, then here again happy. You will get the equitable coloring. And we will encode information about this, whether you can move something or not. We add HBI BJ if you can move one vertex in BI to BJ, which happen only when there exists a vertex B in BI that has no neighbor. In BJ. In such a case, you can move it, right? I mean, since we want to keep it as a proper coloring, you can move it to here only when this doesn't have any neighbor here. Okay. And we say that so we define this diagram. And we say a vertex BI of this diagram is accessible. We give the name to certain, color class of the coloring. If DF has a path from BI to B1. So that means just like here, the vertex, here can be moved. And then if you have a path between here, 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 and you can move one vertex to here, and then another vertex to here, another vertex to here. So if we call this as an accessible, one thing we know is that if BK is accessible, then this G has an equitable K coloring by how I mentioned, by shifting a vertex of BK, a vertex of the bar graph G from each class on the path to the next class on the path. And we say that the PI blocks PJ. If you delete PI, then it does not contain any path from BJ to P1. And one more definition is that an accessible class is, we say, free if it does not block any other accessible class. So you could have P1 and then P2, P3, P4, and then in your TF, your edges could be in this way. And this is accessible, this is accessible, this is accessible. So this blocks this one. Because once you delete this, then there is no path from here to here. On the other hand, this does not block anything else. So this is free, this is not free. Okay. So how do we choose our near equitable K coloring? Among all near equitable K coloring of G, we choose one coloring F with the fewest smallest number of inaccessible, not accessible vertices in this TF. So this is not accessible. So you want to maximize the number of accessible one and minimize the number of non-accessible one. And let's assume that in this coloring you have B1 and B2, BA. These are all accessible. Then BA plus 1 to BK, say, are all not accessible. We know that BK is not accessible, otherwise we are done. So there are such things. Let's assume that this K is same as A plus B. B is K minus A. And moreover, let's assume a bit more that up to B A minus A prime, these are not free. And BA minus A prime plus 1 to here, these are all free. You can just change the index so that these are the free ones and these are the not free ones. And let A be the all vertices in the accessible but not free. No, sorry, all the vertices in accessible one. And A prime is the vertices in free. And let's say B is the vertices in not inaccessible ones. Okay. And this definition is good, but we can actually slightly strengthen what we want to do. So let's say this one doesn't have any neighbor here. This one doesn't have any neighbor here. This one doesn't have any neighbor here. Then, as I mentioned, you can move it here, move it here, move it here. So that's possible until you go to the B1. So you can move, 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 move. However, it's actually possible in a way that this could have some neighbor here. Instead, I mean, here now it doesn't have any neighbor, so that's why we move, right? But even if there is this one edge, so this has only one neighbor, but the then neighbor has no edges here, then we can still move. We can move it to here, and then we move it to here. But while moving it, we have edge, but we know that this will be soon moved. So in that case, this is fine. However, in that case, this digraph does not have any edges from here to here. I mean, unless there are other vertex. It does not guarantee an edge from DF. So we might still be able to do this, even if you don't have a path in the diagram. So we want to also give name to such a thing. And before that, let's say you have some, say, BI, which is subset of A prime. So these are the free one. I mean, this is the free. And we say S is movable. If there exists some J such that if X has no neighbor in this Bj. So meaning that this can be moved to somewhere. If this can be moved to somewhere, then the other vertex can have one edge to here. So we say that on edge xy with x in vi, which is in this free class, and y is in b in excess of 1, is we say that this is a solo edge. If this y has only one neighbor in vi, which is x. So if we, when this situation is good, if you have a solo edge such that the vertex here is movable, if these two conditions both holds, then you can move. So we can actually show what I just said. If xy is a solo edge with x belong to a free accessible class and y is in P and x is movable, then G has an equitable K color. So let's prove this claim. So as x is movable, there is this J which is in bracket A and then which is not I, such that this x has no neighbor in Bj. Then what? We move this x to this Bj, and y into Bi. And what? Then we obtain near equitable A coloring. So now what? You have Bj now have a size r plus 1. And Bi now has size r. P1 has size r minus 1, and Pa plus 1, P K is has size k r plus 1, and everything else has size r. Pl, one vertex is also this has size r minus 1. So this is near equitable coloring, and this is near equitable coloring. So this is near equitable A coloring at prime of this one. The y is added, right? So the x is here, y is here. Y is added. So everything else was A, but the y is added. And also near equitable B coloring. Say G of P minus Y here. But what we know, since this Bi was free in the original coloring, if Pj remains, so Vi changes, but we already had a path from this Pj to P1 in this df. Now everything in the middle does not change. So by using that, you can actually shift one vertex in here to P1 that remained accessible under F prime. Hence, df prime has a path from Bj to P1 Thus, you can turn this coloring F prime into an equitable A color. So this can be turned into the coloring that everything here has same size. Now it's done if we can turn this one into equitable D coloring. But we know for each G, vertex G in some inaccessible color classes B, but you know, A as this PS is inaccessible means that what? If vertex here are here, if this can be moved to one of this, then it gives us the edge, directed edge from here to here, and then directed edge from here to here by the accessibility, and it becomes accessible. That means there is no edge in DF from here to here, meaning that this one must have a neighbor here. As this is inaccessible, this vertex must have a neighbor in each BI in one of A, so this has at least A neighbors in capital A. At least one in B1, B2, B2, B3, BA. Hence, what? Because the number of neighbors in B is strictly smaller than B. So maximum degree of what? G on this B minus Y is strictly smaller than B. Thus, you consider the induction hypothesis. We said that our G was the minimum counterexample. Any subgraph of it, the theorem holds. So this is the strict subgraph. So it yields an equitable B coloring of this part. Then what? You can get the equitable D coloring here. You can color it with B classes of size R. So together with the equitable A coloring of GA union Y, this yields an equitable K coloring of G as desired. This proves the claim. And let's prove one more claim. If we have XY and XY prime are both solo edges with X being in one of the free accessible class, but X is non-movable and Y prime are not edge. So before we have a solo edge and X is movable, then we could move it as I mentioned. But what if this is not movable? Then still we can do something. If there are two solo edges meeting X and Y prime are not adjacent, then he has a near equitable K coloring with more accessible vertex classes than A. So we want to claim this, which will contradict our choice of this F. So we chose F as a near equitable K coloring with S large number of accessible vertex collects as possible, and that was A. But what can we do here? Again, this holds as it is. So what we know is that we consider G, and then you delete Y from B, and then you take the inverse of back. It has maximum degree less than B. So induction hypothesis yields unequitable B coloring of it. Now what we do? We have X. We have Y. We have Y prime. I mean, Y and Y prime could belong to the same color class or a different color class. It doesn't matter. And what we do is X is not movable. Then it has A neighbors in A. So note that B has exactly RB plus 1 vertices, and then deleting Y, this is divisible by B. So all color class here at the same size here. And what we want to claim is that we can even add this X to one of them because it has A neighbors in A, at least. And also Y is a neighbor of X. So it has less than, say, at most K minus A minus 1. So at most B minus 1 neighbors in B minus Y. Thus, what we can add this X to one of the color classes of the above equitable B coloring. So, then what we obtain is we obtain near equitable K coloring. No, D coloring. G, E minus Y union X. And what we do, we replace. So we have a P1, that is R minus 1, P2, PA, then one of them is PI, and then X is kicked out. Now what we do, we replace this PI with PI minus X plus Y. So we add Y. Then this is a give me a moment. Yeah, so this has the size or R minus 1, R. And here you have the size R, and the one class that contains X has R plus 1. So all together, using the above B coloring, we obtain nearly equitable K-coloring for the entire graph. But what do we know? Now, one thing we know is that there must be y prime is somewhere here. It could be y prime is somewhere here. And this y prime, now, this y prime has no neighbors in Vi. Previously, it had only one neighbor, x here. But the x is kicked out and y is inserted. But we know that y and y prime are not adjacent. So it has no neighbors in Vi. Thus, the color class in V minus y containing y2 is now accessible. On the other hand, you know that all color classes in a minus x plus y is still accessible as this Vi is free. It does not block anything. So only Vi changes and everything else is same. And Vi does not block any other classes. So they're still passing this df. So but what we notice is that here's a near equitable K coloring with at least A plus 1 accessible color classes. So that proves the claim. And in particular, that's a contradiction to our choice of F. So that does not hold. And then now the proof remains one thing. We need to show that either we find the solo edge with X is movable, or we find the two solo edges sharing X and then X is not movable and two vertices Y and Y prime are not adjacent. Once we find those, one of those two, then we are done. That shows a contradiction, meaning that there is no minimum counterexample. So maybe we prove the remaining thing in the next video.